In 1915, a British inventor created an engine so revolutionary that military officials declared the test data impossible, yet every number was accurate. His machine burned less petrol, delivered greater force, and stayed cooler than any contemporary design. Authorities suspected faulty instruments. The creator was Harry Ricardo, and his readings told the truth. Britain was fighting the Great War, urgently requiring dependable engines for tanks, lorries, and flying machines. Most power plants overheated, faltered, and squandered critical fuel. Ricardo's experimental prototype, assembled in a humble Sussex workshop, appeared to violate engineering orthodoxy. His breakthrough that genuine power originated from precise fuel-air blending before ignition would ultimately transform mechanical science. Yet initially, only his small circle grasped the magnitude of his achievement. Harry Ralph Ricardo entered the world in 1885 in London. Born into a household that prized innovation and empirical inquiry, he pursued mechanical sciences at Trinity College, Cambridge, where he rapidly developed a fixation on the internal combustion power plant. While fellow students satisfied themselves constructing basic steam experiments, Ricardo devoted evenings dissecting flame fronts, compression mathematics, and thermal losses. He demanded answers: why power plants squandered energy and how to eliminate waste. Following his 1908 graduation, he commenced designing experimental petrol motors for motorcycles and automobiles, concentrating on cylinder performance and controlled combustion. His initial prototypes already surpassed most commercial offerings in output, yet Ricardo harbored little interest in machine sales. What captivated him was combustion itself, the unseen chemical transformation inside metal chambers, converting vapor into movement. When conflict erupted in 1914, Britain's revolutionary weapon, the armored fighting vehicle, faced catastrophic difficulties. The earliest models carried cumbersome, unreliable power plants borrowed from agricultural tractors. They overheated, stopped dead in battlefield mud, and occasionally ignited after mere hours of duty. The military sought assistance from Ricardo's emerging firm, Ricardo Engineering. He accepted, relocated to Shoreham by sea, and initiated what became one of history's most consequential engineering investigations. Within months, Ricardo's modest workshop produced an entirely revolutionary power assembly. Employing meticulous thermal transfer analysis, enhanced fuel-air integration, and a restructured cooling apparatus, his power plant operated for extended periods under demanding loads without overheating. When installed in the Mark V armored vehicle, it functioned flawlessly. Soldiers who had endured months battling temperamental machinery now commanded vehicles that maintained forward momentum under enemy fire. The War Office, initially doubtful, suddenly comprehended Ricardo's accomplishment. His blueprint didn't merely enhance capability, it converted the tank from mechanical burden into trustworthy weapon. For the first time, masked steel could advance confidently across the Western Front. Unlike numerous inventors, Ricardo rejected instinct or fortune as guides. He embraced empirical evidence. He constructed Britain's pioneering scientific power plant testing platforms, documenting pressure oscillations, thermal readings, and combustion velocities with obsessive accuracy. His journals overflowed with calculations connecting fuel chemistry to engine architecture mathematics most contemporary factories never contemplated. Associates observed he approached every power plant as a laboratory subject rather than commercial product. That rigor granted him insight into a challenge afflicting every internal combustion engine of the early 20th century: detonation or knocking. When fuel ignited prematurely, it dissipated power and could obliterate an engine instantly. Ricardo began investigating how compression and fuel characteristics interacted, establishing foundations for what we recognize as octane rating. His investigation demonstrated that by governing fuel burn velocity, engineers could safely extract vastly greater power from identical engine dimensions. By the Great was conclusion. Ricardo's reputation had quietly permeated the engineering community. His redesigned tank power plant became the template for subsequent British armoured machines. More significantly, his mastery of combustion efficiency began influencing aircraft constructors and automobile companies alike. Rolls-Royce, Vauxhall, and Bentley all solicited his counsel during the 1920s. He avoided pursuing contracts or public attention. Instead, he concentrated on perfecting his scientific methodologies, publishing technical documents that resembled physics more than mechanics. Each paragraph supplanted superstition with quantifiable causation. In a discipline once ruled by trial and error, Ricardo introduced systematic order and mathematical precision. In 1919, he incorporated his enterprise as Ricardo and Company Limited, constructing a specialized research installation at Shoreham. There he persisted exploring how fuels responded under pressure and elevated temperatures. Every outcome, every schematic, every malfunction was recorded and examined. His laboratory evolved into a quiet dynamo of British innovation, generating data that would shortly direct engine development globally. What originated as urgent wartime remedy was maturing into a lifetime of scientific discovery. The challenges of knocking, efficiency, and power generation weren't exclusively military matters. They represented the future of transportation itself. Ricardo recognized that as power plants grew faster and more compact, combustion precision would determine advancement. He had elevated the act of burning fuel into rigorous science, and shortly that science would render Britain's engines on land, ocean, and air more formidable than ever previously, following the Great War. Harry Ricardo, standing as one of Britain's foremost combustion authorities, was unquestionably secured. The military had witnessed his TAG power plant's capabilities, and industry began realizing that identical scientific methodology could revolutionize civilian power. His small Shoreham workshop had become a comprehensively equipped research laboratory, a location where power plants were no longer constructed by instinct, but by mathematical calculation. The conflict had imparted Ricardo one paramount lesson: that dependability outweighed raw force. The tanks of 1916 had proven that a power plant functioning in laboratory conditions proved worthless if it collapsed in combat. Consequently, in subsequent years, he dedicated himself to comprehending combustion behavior under every conceivable circumstance: heat, pressure, altitude, and fuel composition. His methods were obsessive yet revolutionary. Where other engineers speculated, Ricardo quantified. He commenced by analyzing detonation causes. The sudden knock destroying pistons wasn't random, as most believed it resulted from unstable fuel igniting irregularly before the spark. Ricardo engineered transparent cylinders and employed optical instruments to observe flames directly. He discovered that combustion chamber geometry, air-fuel mixture turbulence, and petrol volatility all determined engine smoothness. It constituted work no automobile manufacturer possessed patience or precision to execute. But Ricardo did not. By the early 1920s, major British firms dispatched engines to him for evaluation. Rolls-Royce requested his assistance on preliminary aero engine projects, while Vauxhall and Crossley consulted him for enhancing commercial vehicles. His octane number research, a measure of fuel's detonation resistance, became a petroleum industry benchmark. High octane permitted engines to withstand greater compression safely and generate more power. That straightforward relationship altered engine design's trajectory for the remaining century. Simultaneously, Ricardo began investigating diesel power plants. They remained crude and clamorous machines, but he perceived potential in their thermal efficiency. He developed combustion chamber geometries that made diesel burn uniformly, diminishing smoke and increasing output. These experiments established foundations for modern high-speed diesel engines, which would soon dominate commercial transportation. By the mid-1920s, his company, Ricardo and Company Engineers, had matured into one of Britain's most esteemed independent research organizations. Governments, automobile manufacturers, and even aircraft producers submitted designs to Shoreham for testing. Every experiment was documented, every anomaly explained. Ricardo maintained that engineering concerned understanding failure as much as success. If a piston fractured or a valve burned through, he would examine it microscopically until he knew precisely why. The interwar period also saw him advising the Air Ministry, where his fuel behavior knowledge proved vital. Aircraft engines then suffered detonation at high altitudes, where air thinned and cooling diminished. Ricardo's studies led to specialized high-octane fuel development and improved combustion chamber designs, enabling pilots to climb higher and fly faster without destroying power plants. This quiet laboratory and hammer work would later prove decisive when Britain confronted its greatest challenge. Though now among the nation's most respected engineers, Ricardo shunned publicity. He disliked self-promotion and preferred his instruments and apprentices' company to banquets or awards. His laboratory was modest but disciplined, every tool positioned precisely, every test documented. Visitors remarked on the building's calm atmosphere, as if industrial noise had been replaced by scientific precision. By the 1930s, Ricardo's discoveries were shaping not only military design, but also civil progress. His papers on thermal efficiency, fuel injection, and turbulence circulated throughout Europe and America. He collaborated with Shell and BP to develop superior refining techniques, ensuring Britain's petrol supply was cleaner and more stable. When the Royal Navy began fitting diesel engines in submarines, Ricardo's combustion research made them reliable. He had transcended mere engineer status. He had become a teacher of principles. His philosophy was elementary. Every improvement begins with measurement. Guesswork, he stated, is progress's enemy. That conviction resonated through every project bearing his name. As war clouds gathered again over Europe, Ricardo's work assumed fresh urgency. The coming conflict's engines would need to be faster, tougher, and more efficient than ever. The Shoreham laboratories buzzed day and night with experiments. New fuels, new pistons, new cooling methods. Ricardo's team, though small, produced results that influenced aircraft and tank production nationwide. He didn't view himself as part of the war machine, but as part of its survival. He often stated that good engineering saves lives because reliability prevents failure. In 1939, when Britain again found itself at war, his ideas quietly developed over decades became the difference between victory and defeat. By then, the Ministry of Aircraft Production and Royal Air Force relied on Ricardo's combustion control and high-octane fuel research. Every Spitfire and Hurricane ascending into the skies did so with powerplants fine-tuned by principles he had discovered years earlier in his Sussex laboratory. Harry Ricardo's war would not be fought in trenches or cockpits, but in test cells filled with smoke, pressure gauges, and endless data sheets. And it was a war he was uniquely prepared to win when the Second World War commenced in 1939. Harry Ricardo was 54 years old, still active, still inquisitive, and still working late in his Shoreham laboratory most evenings. His interwar research had already shaped Britain's engines, but now his knowledge would help determine a nation's survival. Britain's air defense, mobility, and logistics all depended on fuel efficiency and engine reliability, both fields in which Ricardo had become the quiet authority. A T was outbreak. The Ministry of Aircraft Production turned to him once more. Aircraft engines were being pushed beyond safe thresholds, especially in high-altitude combat. When power plants detonated, they lost power or failed completely, often costing pilots their lives. Ricardo's earlier detonation, compression ratio, and fuel quality work had already proven that the answer lay not in more power, but in superior combustion control. His research became the backbone of Britain's high-octane fuel strategy, collaborating alongside Shell and the Air Ministry. Ricardo's team perfected new fuel formulations that permitted higher compression without knocking. This meant fighter engines such as the Rolls-Royce Merlin used in the Spitfire and Hurricane could produce more power without damage. Those extra revolutions per minute gained through chemistry and precision gave Britain's pilots the vital edge in the skies during the Battle of Britain. The victory was as much a triumph of engineering as of courage. Ricardo's name rarely appeared in wartime newspapers, yet his fingerprints were on nearly every British engine. His firm worked on tank and armoured vehicle power plants, marine diesel units for the Royal Navy, and auxiliary generators for field operations. Each design benefited from his methodical approach: measure, test, refine. His laboratory became a national asset, guarded and operated under government supervision, but always under his quiet leadership. He often said that good engineering wins wars before they start. For him, this meant foresight, solving mechanical problems in the workshop long before they could appear in battle, while aircraft engineers worked on speed and firepower. Ricardo focused on endurance, how to make machines run longer, smoother, and with fewer resources. The results of his fuel research extended beyond combat. The same principles improved lorries, ambulances, and even portable generators used by medics in the field, despite wartime secrecy pressures. Ricardo continued publishing technical papers carefully worded to hide sensitive details while still advancing science. His studies on heat loss, turbulence, and pressure propagation inside cylinders became foundational material for the next generation of engineers. Universities and companies worldwide relied on his data, even if they never knew its military importance. One of his most significant wartime achievements was diesel engine refinement for naval service. Submarines and escort ships required power plants that could run for extended periods at variable loads without overheating. Ricardo's expertise in airflow and cooling made those engines more efficient and reliable. The improvements weren't glamorous, but they saved countless lives at sea. In the war's final years. Ricardo began experimenting with gas turbines, an idea that connected directly back to the combustion principles he had spent decades studying. He saw in them the potential for the next great leap in power generation. Though his own company focused mainly on piston engines, he maintained close contact with teams developing the first jet engines. He admired their ambition, but warned that efficiency, not speed, would define the future. As victory approached in 1945, Ricardo's laboratory remained a place of relentless work rather than celebration. His engineers were already analyzing post-war requirements, civilian transport, rebuilding industry, and converting military research into peaceful applications. He believed the lessons of war should lead to better technology for ordinary life, quieter engines, cleaner fuels, and machines that wasted nothing. Why the conflict's end. Britain's engine technology was among the world's most advanced. Much of that progress could be traced back to Ricardo's insistence that every problem had a measurable solution. The octane system he had pioneered decades earlier was now the international standard. His cooling designs were copied across Europe and America, and his theories of turbulence and combustion dynamics would soon influence rocket and jet propulsion when peace returned. Ricardo was recognized as one of the architects of Britain's wartime engineering strength. Yet he declined honors at first, preferring to return to research. He often said that invention never truly belonged to the inventor, it belonged to the world once proven. What mattered to him was not fame, but function. Harry Ricardo's war had been fought in silence, with equations instead of gunfire and measurements instead of medals. But when Britain's engines roared, it was his science that made them roar longer, louder, and smarter than anyone else's. When peace returned in 1945, Sir Harry Ricardo was already thinking ahead. Britain needed to rebuild its transport, industry, and energy supply, and his laboratory at Shoreham was ready. Instead of designing weapons, he turned his attention to cleaner fuels and quieter power plants that could serve civilian life. Buses, tractors, and industrial generators soon ran on Ricardo-inspired systems that used less fuel and lasted longer. In 1948, he was knighted for his contribution to engineering. He accepted the honor with characteristic modesty, insisting that progress had been a team effort. Those who knew him said the title changed nothing. He still arrived early at the lab, notebook in hand, asking young apprentices what they were measuring that morning. Through the 1950s and 1960s, the world around him shifted from pistons to turbines and from mechanical linkages to electronic control. Yet Ricardo's principles endured. His book, The High-Speed Internal Combustion Engine, remained the standard reference for engineers everywhere, not because it offered formulas, but because it taught how to think, observe, test, quantify, refine. He encouraged collaboration between universities and industry, believing that research meant little if it stayed behind closed doors. Long before environmentalism became a concern, he warned that the engineer's duty was to make machines cleaner and more efficient, that waste in any form was civilization's enemy. Even in his 80s, Ricardo still spent time at the test benches, quietly analyzing pressure traces and noting temperature drops with the same curiosity he'd had as a student at Cambridge. Visitors found it hard to tell where his retirement began, because for him inquiry was simply a way of living. Sir Harry Ricardo died in 1974, aged 89. He left behind no monuments, only motion, engines, textbooks, and a philosophy of precision that shaped the modern world. His work bridged the age of steam, petrol, and jet propulsion, proving that progress depends not on chance, but on measurement. He once wrote, "The engineer's task is not to invent energy, but to prevent its waste. That idea still drives every efficient engine built today." A quiet echo of the man who turned combustion into science and gave the 20th century its rhythm of power. If this story of hidden genius and quiet revolution resonated with you, hit that like button and let us know in the comments what other unsung engineers we should cover next here on to War Rewind. History's greatest breakthroughs often happen in silence. Subscribe so you never miss the next one.